Hello, my name is Korpan. Today I'll be presenting our paper titled Hierarchical Freespace Planning for Navigation in Unfamiliar Worlds. This was work done with Susan L. Epstein at the City University of New York. I'd like to start with a motivating example. Here we have a robot, the red square, and its destination, the yellow star. In the real-world environment, this can be a long distance, 65 meters in this example. And for industrial robots, like the ones you see here, that's outside of their perceptual range. In fact, the white rectangle you see is the robot's knowledge of the world if it doesn't have access to a map. This world is much more complex. This is G5, the 5th floor of a large office building the size of a city block in Manhattan. There's many challenges, like narrow doorways that only allow a few inches of clearance on either side of the robot. There's also jogs and support columns like the ones I highlighted in pink. And so this task requires careful maneuvering, learning from noisy or incomplete perception data, exploring only when needed, and flexibly planning to get to a destination. So let's say the robot did have access to this map. Well, there's several possible paths it could take, like these. Our approach is different. Our system is called Semaphore, and it plans hierarchically in a spatial model. Here we have a model of local connectivity. And here's a second model of global connectivity, where we can also construct a plan. It's expensive to create an accurate metric map, but without such a map, navigation is much more difficult. Semaphore is a cognitively based navigator that uses models of free space that focus on where the robot can move, not what impedes it. And so Semaphore starts with initial global exploration and then constructs free space models from that exploration. Once it begins to pursue a target, it can then create a hierarchical free space plan and operationalize each plan step at execution time. Once it completes its plan but has not reached its target, it can use local exploration. And once it reaches a target or a decision limit, we update the free space model and then start to pursue the next target. And so the thesis of this work is that models of connected free space based only on onboard rangefinder data support effective planning in an unfamiliar world. Semaphore is a cognitively based system. It uses a hierarchical decision-making architecture, and it learns a spatial model in real time. The spatial model consists of spatial affordances. These are features that we expect to facilitate navigation that will generalize over the robot's experiences and will be memory efficient. The spatial model is learned from initial exploration, but then incrementally updated later during target-driven travel. Here's a spatial affordance called a region. It's a circle that represents unobstructed free space. From a set of regions, we can learn a skeleton. This is a graph-like structure that creates an edge between two regions if the robot ever traveled between them. Given the spatial model, Semaphore's plan is a hierarchical sequence of spatial affordances. Now, I've talked about Semaphore's spatial model, but now let me talk about how we do our initial exploration. Our algorithm is called HLE. It's a high-level global exploration algorithm that seeks long stretches of free space that we call highways. Here you can see an example of our robot's rangefinder data, and we've highlighted one of the long rays in that data that we can then use to find these long stretches of free space. HLE is intentionally time-limited, and it seeks global connectivity. These are the intersections between the highways. We limit its time so that we can try to balance the amount of time we explore with the amount of information we can learn about a world for navigation later on. So here's a video. The robot starts at the S. As it explores the environment, you'll see it fill in with white, blue, and purple. This video is being shown at 10 times speed. In real time, this takes 30 minutes, and it is because it's the size of a city block, right? This is a large building. You'll notice that it's focused on these long stretches. It's not going to every one of the rooms to try to map them out. If I skip ahead in the video, you'll see it learns the regions in the spatial model at the end. And then later on, it will repeatedly update this initial model during target-driven travel. HLE not only focuses on horizontal and vertical highways, but it can also capture diagonals. Now, let's say later on during that target-driven travel, the target is not captured within the spatial model. And so what can we do instead? Well, we can use local exploration. So our algorithm is called LLE. It's decision limited and target driven, and it explores when the plan finishes. It's based on the spatial model, and it can trigger updates to that model and then replan in the updated model. So here's another video. The red circle will follow the robot as it navigates. The green circles are regions, and the pink dot is its target. I'll pause it right here when it reaches the end of its plan. At this point, the target is still outside of sensor range, and it doesn't have a region in this room or previous experience in this room to get to the target. At this point, LLE will trigger. It will find a long ray in the robot's perceptual history and then try to follow that ray to explore in the direction of the target. It successfully finds a ray. It's able to follow that ray, get to the target. This video is in real time, and you'll see that it only takes a few seconds for it to update its model and plan to get to its next target. Now, how do we actually create these plans? Well, we use FreeSpace-based planning. We plan directly in the FreeSpace model, but first we have to transform that model into a graph. So let's start with a skeleton like this that's been learned from exploration, and then we can chart it into a graph like this, where the nodes are regions, and on each edge, we can label it with a refined version of the path to travel between those two regions. We can then use that graph to create a hierarchical plan. Let's say we have a robot at the bottom and a target at the top. Well, we can create a plan that takes us to those regions. That plan can then be operationalized at execution time. This operationalization is intended to allow flexibility in the robot's action selection so that we can contend with any noise in the model, but also take any novel shortcuts. So here we have an example where we have a plan that goes from A to B to C. Notice that there's no edge between A and C because the robot never traveled directly between them, so we didn't create an edge. But when the robot gets to region A, it can sense region C and move directly there, taking a novel shortcut. This operationalization also allows us to balance the current perception with past knowledge. And so here we have an example where the robot's at region S trying to get to region T. The edge appears to go through this obstruction, but we can rely on a previous path that connected these two regions to travel between them instead. The second FreeSpace planner is based on the highways learned during global exploration. So we start with a grid that's filled in from that travel. We can then refine that grid to learn highways and intersections. And then from there, we can learn a highway graph. Given this graph, we can then plan. So the robot can start here, follow the sequence of intersections in the highway graph to get as close as it can to the target. And then this last bit, it can rely on the skeleton and supplement its highway graph with the skeleton graph. We evaluated this work in simulation with noisy sensors and actuators. We looked at 5 sequences of 40 targets, and we averaged over all of those sequences. We looked at 3 real-world environments, M5, the 5th floor of the Museum of Modern Art in New York City, H10, a large office building, and G5 that I showed you earlier. These differ in both size and complexity. We looked at different versions of our system with exploration and planning, and we found that success rate improved with exploration and planning together in H10 and G5, the larger complex environments, to achieve about 90% success. In M5, planning and exploration were less necessary. We also looked at time to travel to a target, which we want to reduce, and we found that planning and exploration reduced it in all 3 environments. Similarly, distance to a target also reduced in all 3 environments with exploration and planning. We looked at coverage, which is the percentage of free space in an environment, and we found that exploration improves coverage. The average decision time is about half a second, so nearly real time. And the planning in these free space models was about 90% faster than a metric map-based cost graph. Our contributions here were 2 opportunistic exploration algorithms, hierarchical free space planners that are operationalized at execution time. Our current work is in natural language explanations and in dynamic allocation for exploration and imperfect localization. Our take-home message is that a robot controller that explores when needed, focuses on free space and plans hierarchically, supports robust navigation in complex, unfamiliar worlds. Thank you.